All right, welcome back to the last lecture for the course. We won't be doing chapter 8 this session, so we'll just switch over and talk about correlation and regression because I think it's important that you see at least the basic idea between correlations and regressions in general. Okay, so we won't do the entirety of chapter 9, we'll just do the first two sections, 9.1 and 9.2, and that's where we'll end for the course. Okay. So let's get into the material. So let's talk about correlation regression. The first thing we need to talk about is what do we mean by correlation, right? So we'll talk about what linear correlation is, what independent and dependent variables are, and the different types of correlation. Then we'll talk about the technical details of how do you find a correlation coefficient. So the formula seems a bit intimidating, but once you see what the pieces are and how they fit together, it becomes fairly straightforward. Then obviously we want to test uh, hypothesis about population correlation, and there's two ways we'll do it, right? Using a table, and we'll use a hypothesis test where we construct a test statistic and then determine if the correlation is significant or not. And finally, we'll finish this section with a very important notion that correlation does not suggest causation, right? Those two are separate ideas. Just because two variables are correlated doesn't mean that one causes the other. Okay, so that's the big roadmap for this section of it. And very simply, let's start with an introduction of correlation, right? A correlation is basically we're trying to establish a relationship between two different variables, right? So the data when we are considering correlations is in the form of ordered pairs. Ordered pairs as in like every data point consists of two coordinates, an x coordinate and a y coordinate. The x is considered the independent or explanatory variable, and y is called the dependent or the response variable. So we want to understand how these two variables x and y are related. So what do we mean by that? So we want to know if x changes by a small amount, what happens to y? That's why it's called explanatory and response, right? If I change the explanatory variable by a small amount, what is the response in the y variable? And that tells us whether these two variables are in fact, first of all, related. And if we establish that they're related, then what kind of relation they have, right? That's what we're trying to do with correlation. And the usual way in which we try to establish this, the graphical visual way of seeing whether there is some kind of correlation, is to use a scatter plot. Okay. So a scatter plot gives us a visual idea as to whether two variables are correlated, whether a linear correlation exists between two variables. Right? Linear correlation essentially means that we're trying to fit a straight line through the data set. So here's an example. So we have a paired data set. So when x is 1, y is -4. That's why these are paired. So each data point is a pair of observations. So when x is 1, we observe that y is -4. So that's this point right here. Let me get a pen. So that's this point right here. When x is 1, so x is 1, y is -4. That's that point there. When x is 2, y is -2. When x is 3, y is -1. And so we have the scatter plot. Okay, straight away you can see that there's some kind of linear relationship between them, right? There's some kind of relation between these two variables, and it's kind of linear in the sense that if I try to draw a straight line through these points, it might not be exactly a straight line, but you get something approximating a straight line in there, right? And what does it suggest? It suggests that as x keeps going up, y also keeps going up. Right? That's what it means for this to have a positive linear correlation, is that as x is increasing, as I change the value of x in an increasing way, as I keep increasing the value of x, the value of y is also increasing. Right? So -4 is smaller than -2, -2 is smaller than -1, and 0 is greater than -1, and 2 is greater than 0. So now we are able to establish that there's some kind of relationship between x and y. As x is increasing, y is also increasing. Okay. And now we've established that these two variables might be correlated. There might be some level of quote unquote linear correlation between these two variables. Okay. So we'll talk about different types of correlation. The first one is what we call negative linear correlation. So what is negative linear correlation? So if you look at this line, if I try to fit a line through that, it looks like this. So what does this suggest? So as x values are increasing, as I move along this x-axis, y is decreasing, right? As x increases, y tends to decrease, and this kind of this type of correlation is what we call a negative linear correlation. The negative part of it is that as the x variable is increasing, the y variable is decreasing, so that's negative. The linear part of it is that it seems to decrease in a straight line way, in a linear way. So that's the linear part of it. And they're correlated, as in like when X is moving about, Y is also responding to it. So there is some kind of correlation, some movement. Uh, uh, when one variable moves, the other variable is also moved. The second type of correlation is what we've already seen in the previous example, this kind of positive linear correlation. Is positive in the sense that as X is increasing, Y is also increasing, right? It's linear in the sense that it seems to have linear response. There's an imaginary straight line passing through it, and we're getting some kind of a linear response, and there is correlation between them. Obviously, these two variables are related. This is a case when there is no correlation. So X is increasing, when X is increasing, sometimes Y goes up, sometimes Y comes down. There's no clear trend in this, right? So it's all just scattered. There's no clear pattern which emerges in the data. So there is no correlation between these two variables, no meaningful correlation that we can derive between these two variables. And here we have a non-linear correlation. So what does it mean? So as X increases, up to a certain point, Y increases, okay? So up to this point here, as I increase the value of X, Y is also increasing. But if I go beyond that and start increasing the value of X beyond that, Y is going to decrease. So it's not some kind of linear path where I increase X, Y increases, or I increase X, Y decreases, as we have with linear correlation. That's what we mean by linear, in the sense that there's only one direction to it, right? A straight line points only in one direction. So in a certain, that's what we mean, right? So as X increases, if Y continues to increase, then we have positive correlation. If X increases and Y decreases, then we have negative linear correlation. If X increases and Y doesn't have any meaningful pattern emerging, there's no meaningful response in Y emerging, then we have no correlation between these two variables. And finally, if X increases and Y increases up to a certain point, then decreases, then increases, it could do a lot of different things, then we might have what we call nonlinear correlation. That these two variables are correlated, but there's some tipping points, there's some inflection points here and there where the behavior of the curve itself is changing. Okay. All right. So let's use an example to get this ball rolling on correlation. So an economist wants to know whether a country's GDP is related to its carbon dioxide emissions, right? So around climate change, you might want to know what is the impact if we cut back on carbon dioxide emissions by a small amount, so that we reduce the amount of global warming and climate change, then what is the impact on GDP? Okay, so what do we have here? So the economist goes and collects the data, right? This is coming from the World Bank and the US EIA, which is the US Energy Information Administration. So this is real world data. So what it suggests is that these are the pairs of variables we are considering, and we want to establish if they're correlated. When we say correlation, all we want to know is that first of all, we want to know if there is a relationship between the GDP of a country and the amount of carbon dioxide emissions, right? So here we have a paid data set. So when the GDP of the country is $1.6 trillion, the carbon dioxide emissions at that point were 428.2 metric tons, millions of metric tons, right? So this measured in trillions, it's measured in millions of metric tons. So when the size of the economy grows, so 3.6 trillion, then the emission level is 828.8, and we go down this list, right? So we have a paid data set. So we have two variables measured at the same point in time. So they are a paired data set. And now we want to know whether there's some kind of correlation between them. So let's look at a scatter plot of this, right? On the x-axis, we are measuring GDP, and on y-axis, we are measuring CO2 emissions, and we can plot these points. So when x is 1.6, y is 428.2, so we plotted this 1.6 will be somewhere there, so 428.2, and then so on and so forth. We're plotting when x is 3.6, then it's 828.8, so this is 3.6, so this is 828.8, and we can plot all these different points on there. And what do we see? There seems to be a slight positive correlation between these two variables. What does it mean? So as the GDP level of the country goes up, as the country gets richer, the carbon dioxide emissions that that country emits also is going up. So X and Y are related. First of all, that we can see that they seem to be related. The second thing is to determine the direction of the relation, and this is seemingly a positive linear correlation. Appears to be positive linear correlation. But now we are just eyeballing it using the scatter plot. So when we get into the technical details of it, we can actually calculate numbers which tell us what the correlation is precisely. But just by looking at the scatter plot, you can start off your analysis by saying, okay, looks like there is some positive correlation. Let's figure out how strong or weak, or if there is in a technical sense later on. Okay. All right. So how do we do this? So the technical way we do this is by calculating what we call the correlation coefficient, right? The correlation coefficient tells us not only the direction of the correlation, whether it's positive, negative, or no correlation, it also tells us the strength of the correlation, right? Higher the correlation coefficient is, the stronger that relationship is, right? So the symbol R is what we use to represent the sample correlation coefficient, and R is calculated with using this mess of a formula here, which is not very complicated. Written this way, it seems very complicated. All this is saying is that we measure the covariance between X and Y, right? On the numerator, we have the covariance between X and Y over the standard deviation of X times the standard deviation of Y. Okay, this is the simpler formula for the correlation coefficient. But if you expand this formulas out for what the covariance formula is, what the standard deviation formula is, and what the standard deviation of Y formula is, as you can tell here, you get this slightly more complicated formulation. The way it's written seems slightly more complicated, but once you know this formula, and this formula is in front of you, obviously, when you're taking the exam and when you're doing this math, generally speaking, so you can just make sure that you plug in all the right things in the right places. So the population correlation coefficient is represented by this number rho, and the sample correlation coefficient is represented by R, right? The difference being if the data set is a population data set or a sample data set. If the population data set, then we use rho as the correlation coefficient, this Greek letter here. And if you're working with sample data, then we calculate what's known as R, which is a sample correlation coefficient. But the crucial element of it, you need to obviously know the formula in order to calculate R, but the crucial element of it is to recognize that R is going to tell us what the direction of the correlation is, whether it's positive or negative, and also give us an idea about the strength of the relationship between the correlation between these two variables. Okay. So when we calculate the correlation coefficient, it's always going to end up being a number between -1 and +1. Okay, it's always going to be in this range of -1 to 1. So if you're working with correlation coefficient, and if you calculate it and it turns out it's some number which is not in this range of -1 to 1, that means that you've done something wrong somewhere. Okay. So correlation coefficient is always going to be between -1 to 1. And let's talk about the ends. If R is -1, there's two elements to it. First of all, the negative sign indicates that there is negative correlation. And the 1 here says that this is perfect negative correlation. So what does it mean for R to be -1? It means that if X changes by 1 unit, Y falls by 1 unit, right? This is perfect negative correlation where there's one-to-one mirroring movement and the direction of the movement is negative, right? As X is increasing, Y is decreasing. So that's why it's negative correlation. And the negative sign here on the correlation coefficient tells us whether it's negative or positive correlation. So if R turns out to be a negative number, then you have negative correlation. And then this second part of it tells us the magnitude of the relationship. In its limit, when R is -1, we have what we call perfect negative correlation, whereas X increases, Y decreases, and it decreases 1 to 1. If X goes up by 10%, Y comes down by 10%. If X increases by 1 unit, Y falls by 1 unit. R is equal to 0 basically means that there's no linear correlation, right? We might get like a scatter plot like this where there's no discernible relationship between X and Y. So when X is here, Y is this much. When X is here, Y is this much. So if you add only these two data points, you think that there's negative correlation. But once you add in the third, there is like this, then it goes up, then it comes down, then goes up, then comes down. So you get no meaningful linear trend in this data set, right? So as X goes up, Y just flutters about all over the place. And finally, at the right end of it, if R is equal to 1, then we get a perfect positive correlation. The positive sign indicates that it's a positive correlation. So what does it mean for it to be positively correlated? It means that as X goes up, y goes up. And how much is if x changes by 1 unit, y changes by 1 unit. That's what this number r represents. So you can have any number for the correlation coefficient between -1 and 1. And depending on the sign of the correlation coefficient, you can establish whether there is positive or negative correlation. And depending on the magnitude of the correlation coefficient, you can establish the strength of the relationship between the two variables. Okay. So here's a case where R is negative 0.91. What kind of correlation is here? First of all, R is negative, so we know that there's negative correlation, and the magnitude here is 0.91. So given that the magnitude is 0.91, it's very close to 1, it suggests that it might not be perfect linear negative correlation, but it's very strong linear negative correlation, right? R is 0.88, again, same, the closer R is to either -1 or +1, that's established the strength of the relationship. So in here, R is positive, so that tells us we might have positive correlation, and it's strong positive correlation because the magnitude here of R is 0.88. R is negative 0.42. Again, we have like a a trend like this where R is positive, so it suggests that we have positive correlation, but it's fairly weak because the magnitude is 0.42. It's not very close to 1. It's closer to 0 than it is to 1, so we call this weak positive correlation. And here R is 0.07. So R here is basically very close to 0, and then we get a scatter plot like this. And it suggests that there is no correlation between x and y, that there is no relationship, no discernible linear relationship between x and y. Okay. All right. So how do I go about calculating the correlation coefficient? I have a recipe book here, right? Have the formula. You just have to find the different elements of that formula. So first of all, we find the sum of the x values, sigma x, that represents sum of x values. Then you sum up all the y values, sigma y, that's the sum of the y values. Then you multiply x times y and add all of them up. So multiply each value by its corresponding y value. So you take each x value multiplied by its y value and sum up that column. I'll show you an example in just a second. Then square each of the x terms and add them all up. So x square, first take each x, square it, and then add that column up. Then take each y, square it, and add that column up, and then use these 5 sums to plug in the right places. So you have sum of sigma xy, which you calculated here in step 3. So you plug that in. N is the number of data pairs you have. So n times sigma xy minus sigma x times sigma y. So the sum of x's times the sum of y over the square root where n times sigma x squared that you calculated here minus sigma x squared. So make sure that you don't get confused. Here it says that it's the sum of the x squared terms. So you take each value of x, square it, sum that column. That's the number which goes in here. And this is sigma x squared, where you add up all the x's first, take the sum and square the sum, right? And again, here is sigma y squared minus sigma y whole square. Okay. So for our example here, I've done this exercise. So, we have x and y values and I have this table. So the simplest way to do this is that first you have all your x values, you have all your y values, you do x times y. So you do x, the first column is x times y. So it's 1.6 times 428.2, which is 685.12. That's the first entry here. Then it's 3.6 times 828.8. So that's 2,983.68. So that's all these xy values. X squared, so you take each value of x and square it. So 1.6 squared is 2.56, 3.6 squared is 12.96, 4.9 squared is 24.1, so on and so forth. So you get a column of x squared values, then you get a column of y square values. So you take each value, each y, and multiply and square it. So 428.2 squared is 183,355.24. 828.8 squared is 686,909.44, and so on. Okay. The crucial thing is that once you have this table, you want the column sums. So the sum of all x's is given by this column sum, 23.1. Sum of all y's is adding up all these y values, which is 5,554. Sum of xy is 15,573.71. Sum of x squared is 67.35. Sum of y squared is 3,775,000. Whatever. Okay. So now that you have these 5 numbers, it's just about putting it into the formula. So first of all, how many n's do we, what is the value of n? N is the number of data pairs we have. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n here is 10, right? So sigma x is, so if you want, you can write it out like this. Sigma x is 23.1. So this is where I'm getting that from. Sigma y is 5,554. This is where I'm getting that from. And sigma xy is the sum of the column of xy. So that's this number. Sigma x square is 32.24 and sigma y square is this 3 million thing. And then I need to just plug it into the correlation formula, right? So the correlation formula, n is 10. Sigma xy is this number. So 10 times this number minus sigma x times sigma y. Sigma x here is 23.1 times sigma y 5,554. So you first multiply these two, take that difference. Then in the denominator is the square root of n, which is 10, times sigma x squared. So sigma x squared is this term here, 32.54. Okay. No. Oh, 67.35. So sorry, I have a typo here. This is not 32.44, it's 67.35 minus sigma x squared. So sigma x, the sum of the x's is 23.1 squared times the square root of 10 times sigma y squared, which is this, minus sigma y, which is 5,554 squared. Okay, you just simplify all of this out, and what you get here is 0.882 as the correlation coefficient. So what does it tell us? R being 0.882 suggests, first of all, that R is positive. So we have a positive correlation. We have positive correlation, and this number here is 0.882, which is fairly close to 1, suggests that we have strong positive linear correlation, which gives us the indication that as GDP increases, the carbon dioxide emission levels also increase, and we have strong positive correlation between these two. Okay. So one thing to mention is that it doesn't go just in one direction. So as GDP increases, carbon dioxide emissions increases. At the same time, it suggests that as GDP decreases, carbon dioxide emissions also decrease, right? Okay. It's just establishing that there is a positive relationship between these two. So whatever one variable, whatever is the direction of movement in one variable, the other variable also mimics the same direction of movement, right? That's what it means to have positive correlation, because if x goes up, y also goes up, and negative correlation suggests that as x goes up, y comes down. Okay. All right. So there's two ways to test a population correlation coefficient, whether it's significant or not. So as usual, to conduct this test, we need to first specify level of significance. What level of confidence do we want to conduct this test at? We use this table 11 in Appendix B. So I'll try to post the table. But when you're doing these questions, the table should pop up. When it pops up, just make sure you save a copy of it. So during the exam, you're not looking for it as well. Okay. So if R is greater than the critical value, then there is enough evidence that to decide that the correlation coefficient is significant. Okay. So in this table, we have different confidence levels, right? Alpha here is 0.05, alpha here is 0.01. So there's a 5% significance level, there's a 1% significance level, right? Determine whether rho is significant for 5 pairs of data at level of significance of alpha equal to 0.01. So when there's 5 pairs of data, you look in row 5, okay? And if the significance level is 0.01, then the critical value here is 0.959. As long as the correlation coefficient that you're calculating is greater than 0.959, we say that it's significant. If it's less than 0.959, it's not significant. Okay. So the critical value that you pick off that table is you look in the row where the number of pairs is, if there's 5 data sets, then it's 5. And then alpha here is the critical value is 0.01. So if your correlation coefficient is greater than 0.959, then the correlation is significant. If it's less than that, when the calculated correlation coefficient is less than that, then the correlation is not significant. Okay. So how do you do this? First, you determine n. N is the number of paired data sets. Then you identify alpha. You specify the level of significance. What do you want to do at the 5%, 1%? What is it? you have to find the critical value. You just pick it off the table using these two things. So the right row is given by n. Here, if n is 5, then we need to look in this row. And the right column is given by alpha, the level of significance. So if I'm doing a 1% test, then the critical value here is 0.959 for this situation. So if the calculated correlation coefficient is greater than the critical value, then the correlation is significant. Otherwise, there's not enough evidence to support that the correlation is significant. Okay, and then you can interpret that decision. So here's a example. So I have this XY data set. So obviously I have 25 pairs of data, and I calculated R. How do I get this number? I did the exercise that I did previously using this table. I essentially plug in everything like I did here. So I have X, Y, this two columns are given to me. So I sum all the X's, I sum all the Y's, then I find X, Y, sum that column, then I find X square, sum that column, then I find Y square, sum that column, and plug it into this formula here. Okay. And I've done all of that, and it turns out that I calculated that R here is 0.979, and I want to know whether this is significant correlation. Can I consider this correlation to be significant or not at the 5% level when alpha is 0.05? So I have R, I have N, I have alpha. All I need to do is look for the critical value in my table. So how do I look for the critical value? So when N is 25, look in row 25, and the column is 0.05. So I look in the first column where alpha is 0.05. And what is the critical value here? 0.396. Okay. So critical value here is 0.396. My calculated correlation coefficient is 0.979. It's obviously greater than 0.396. So what does it suggest? That there is enough evidence at the 5% level of significance, the correlation coefficient, that there's significant linear correlation between the duration of these two variables, right? Between duration and time of these eruptions of Old Faithful. Okay. All right. Makes sense. I hope that's clear. You can use this table to basically establish whether a correlation between two variables is significant or not. Okay. Okay. So the other thing that we can do here is to do hypothesis testing, right? If you make a hypothesis about the correlation coefficient, you can use a test statistic and conduct a hypothesis test as well. Okay, so how do we go about this? A hypothesis test, as usual, can be one tail or two tail, depending on, we've already discussed this. So when do we conduct a left tail test? So if if the hypothesis is that sigma is greater than or equal to 0. So what is the claim when we are saying the correlation is greater than or equal to 0? We are saying that there is no significant negative correlation, right? And the alternative is obviously that rho is less than 0. I keep saying sigma. Rho is greater than or equal to 0, suggesting that there is no significant negative correlation. And the alternative is rho is less than 0. And as usual, the direction in the alternative hypothesis tells us the direction of the test. So given that rho is less than 0, the less than sign indicates that we have to do a left tail test. Okay. A right tail test when the claim is what? That rho is less than or equal to 0, that there is no significant positive correlation. We are claiming that these two variables are not related do not have positive significant correlation. So what is the counterclaim? That they do have significant positive correlation. So here is a greater than sign, suggesting that it's a right tail test. And when you do a two tail test, when rho is equal to 0, that there is no significant correlation, and the alternative is rho is not equal to 0, which suggests that there is significant correlation between the two. Okay? So this t-test that we use for the correlation coefficient can be used to test whether the correlation between any two variables is significant or not. Okay? The test statistic is what we call R here. The test statistic is T. Sorry. And the way we calculate this is using this formula where we take the calculated correlation coefficient and divide by the standard deviation of that correlation coefficient. And so we have the standard test statistic, right? So R over standard deviation of R, but the formula is basically R over the square root of 1 minus R squared divided by n minus 2. And the crucial thing here is to recognize that the degrees of freedom that you use when you're testing for the correlation coefficient using a t-table is n minus 2. It's not n minus 1 like we're used to, but n minus 2. Okay, so the rest of the testing procedure is still the same. We just calculate the test statistic and see whether it's in the rejection region or not, and then you go on your merry way. Okay, so in our context, we are only going to do two-tail hypothesis tests for rho. So we're just going to consider this one situation where we are just testing to see if there is any significant correlation or not. We are not particularly concerned with whether it's positive or negative. All we want to know is whether there is any correlation to begin with or not. Okay. So again, as usual, I have a recipe book here for how you do hypothesis testing for a correlation coefficient. First, you state the null and the alternative hypothesis. Then you identify alpha, the level of the test. So at what level of significance you want to do the test. Calculate the degrees of freedom, where n is the number of paired data sets, where n is the number of data points you have. N minus 2 is now the degrees of freedom. So just make sure that you do that you do n minus 2, not n minus 1 anymore. And then we use we find the critical values or rejection regions based on the t-table, and we find the test statistic, right? So in this particular case, the test statistic is given by R over square root of 1 minus R square divided by n minus 2, where R here is the correlation coefficient that you calculated, okay? And then you make the decision whether to reject or fail to reject the null hypothesis. If T is in the rejection region, obviously reject the null. Otherwise, you fail to reject the null hypothesis. Okay, so we know all of how to do the rest of it. The only difference is two things. The test statistic is this formula. I would recommend that you write down these formulas on a piece of paper so you have it available when you're taking the test and you're not too flustered about it then as to what the formula is. Because and the second thing to recognize here is that when you're testing for the population correlation, the degrees of freedom are not n minus 1, but rather n minus 2. Okay. Okay. So here's an example that we already had. So we already calculated R, right? Again, if you want to know where R is, go back a few slides. We had the same data between GDP and CO2 emissions, and we calculated R to be 0.882. We want to test the significance of this correlation coefficient, and we want to do this test at the 5% level. Okay, so there's two ways. Either you can look through the table and figure it out, or you conduct the test yourself. So what is the null and the alternative? The null hypothesis is that there is no correlation, that rho is 0. The alternative is obviously that there is some correlation, that rho is strictly not equal to 0, is something other than 0. What is alpha here? Alpha here is 5%, so 0.05. And now the degrees of freedom are n minus 2. So degrees of freedom are now 8. So based on alpha equal to 0.05 and degrees of freedom being 8, we go into the t-table, right? We go into the t-table and find the rejection region. So where half of it is in the left tail, half of it is in the right tail, you know how to do this. And you find that the t critical value is negative 2.306 in the left tail and 2.306 in the right tail, right? So if the test statistic that we calculate in the next step is inside either of these rejection regions, then you reject the null hypothesis. If it's not in the rejection region, then you fail to reject the null. Okay, so now we calculate the test statistic. How do we calculate this test statistic? The formula is R over the square root of 1 minus R squared divided by n minus 2. R we calculated was 0.882, 1 minus 0.882 square divided by n minus 2, 10 minus 2, 8, and this turns out to be 5.294. Okay. So once we have this, we want to know whether this test statistic is in the rejection region or not. So 5.294 is here, is squarely within the rejection region. So what is your decision? You reject the null hypothesis. So at the 5% level of significance, you can squarely reject the null hypothesis that there is no significant correlation between GDP and carbon dioxide emissions. Okay. So there's two ways to test for significance with correlation coefficients. One is to just look through the table that we did, the first method. The second method is to conduct a hypothesis test. The usual methods are in play, and we only do a two-tail test for the correlation coefficient. Rho is equal to 0, rho not equal to 0. Alpha is 0.05. Degrees of freedom are 8. And then you can use that to find the critical values, t0 is negative 3.0306. Calculate the test statistic, which is r over 1 minus r squared divided by n minus 2, with the square root of that. So you find the test statistic and figure out whether the test statistic is inside the rejection region or not. If it is in the rejection region, you reject the null hypothesis. If it's not, you fail to reject the null and go about your way. Okay? All right. The last thing I want to mention in this section is this discussion between correlation and causation. Okay? This is a very important idea in statistics. And the big thing, the big banner headline that you need to take away from this is that correlation does not imply causation. Okay? Just because two variables are correlated with each other, which is to say they seem to move, when one moves, the other seems to move along with it, just because the correlation, there is some correlation between two variables, it doesn't mean that the change in one variable is causing the change in the other one. Correlation is not the same as causation. We can't use this method to establish cause and effect relationships. We can merely come to the conclusion that these two variables are related in some way. Now, if one is changing, is the other changing? If the other is changing, is the previous one changing? We don't know that just yet. Okay, so if there is significant correlation between two variables, there is obviously there are many things to consider. Is a change in X causing a change in Y? Does Y cause X? So there could be reverse cause and effect relationship. These two variables are just moving with each other, right? So in our case, we know that GDP and carbon dioxide emissions are correlated and correlated positively, right? So as countries get richer, what we are establishing is that there's a positive correlation, which means that if a country is richer, it has higher carbon dioxide emissions. If a country is poorer, it has lower carbon dioxide emissions. But we don't know if the higher carbon dioxide emissions are because a country is richer, or whether the country is richer because it has higher carbon dioxide emissions, right? It could be the case that the country is a rich country, has a lot of consumption, so people can buy a lot of things. Because they can buy a lot of things, a lot of things get produced, and that in turn raises the carbon dioxide emissions. Or it could be the case that a lot of things get produced first, and that results in higher carbon dioxide emissions, but at the same time, the level of wealth in the country also goes up, so GDP goes up. So we don't know which one is causing the other. All we know is that these two variables are related, and that's a crucial thing to recognize, that correlation is not causation, right? And there could be something else completely different, right? A third variable is causing both of these to move in the same direction, right? That carbon dioxide emissions and GDP is moving in the same direction because of a completely third variable. They're related only in the way that they're related to the third variable, right? So, and the fourth thing to consider is that this relationship could be spurious, right? There's this entire class of what we call spurious correlations, where it's just merely coincidental that these two variables seem to be related to each other, but there's no reason that they are, right? There's no discernible economic reason on which to base this thing. So even though when two variables are correlated, that's fine. That gives us some information that these two variables are related to each other in some way. We can't then straight away jump to the conclusion that one variable causes a change in the other. A change in one variable causes a change in the other, because you have to consider the direction of the causation. X could cause Y, but Y could cause X as well. That's why they're related. So that's one thing to consider. The second thing to consider is that the presence of a completely different variable, a third variable, which pushes both X and Y in the same direction. So that causes a relationship to develop between X and Y, even though they don't have a direct relationship with each other. They're intertwined because they are related to a third variable. And there is always the consideration to be had that the correlation is just spurious, that it's just coincidence, that what you were observing in this relationship is just mere coincidence. Okay. So that concludes what I want to talk about in section 9.1. So we understood what linear correlation is. We understood what the different types of correlation are. We figured out how to calculate a correlation coefficient. We found two tests to test whether the correlation is significant. One is using the table directly. The other is to do a straightforward hypothesis test using a test statistic. And finally, this entire discussion around that correlation is not equal to causation. Okay. correlation could be the starting point to pin down causal effects, but it is not the end point. It's merely the starting point. All right. The next thing and the last thing that we'll do for this entire course is this notion of linear regression. Okay. So inside linear regression, the thing we are trying to figure out is to fit a straight line through a paid data set in order to establish some trend. And using this regression equation, we can do some predictions for Y. Okay. All right. Let's start with the basics. Okay. So now we have X and Y. There's two variables, X and Y, and these are paired data sets. So when X is this much, Y is this much. So that's where this point is coming from. When X is this much, Y is this much, and so on. Okay. Now we have the scatter plot here. And just by looking at the scatter plot, we can tell that there seems to be some positive relationship between X and Y. Because as X is going up, looks like it's going up, generally speaking. Okay. Now, with the regression model, all we are trying to do is to find a line which goes through that. So find the equation of this line which slices through that data set, and uh, we want to use certain criteria to find the line, right? So, based on this, right, if I choose any 2 points, I can draw a regression line like this. I can draw a regression line like this. I could use these 2 points, and I would get a regression line like this. If I use these 3 points, the regression line would be like that. The point is, what is the line of best fit which goes through this data set, which establishes this relationship? Okay. Once we have an equation for this line, we know how Y and X are related, at least on an average level, we know how Y and X are related. So now we can use different, so what will Y be if X is this much? Okay. Now I don't know, right? Because I don't have a data point for when X is this much, I don't know what Y will be. But if we have a regression line and I know X is this much, then I can predict using my line that Y will be this much. Okay, that's the crucial reason for why to use a regression line, is that it lets us predict the value of Y for a given value of X. Okay. The second thing to recognize is what we call the residual. Okay, the residual is what is unexplained. Okay, so suppose we have this regression line XY, so these are the different data points, right? So based on this, when X is this much, when let's say X is at X1, we know that Y is at Y1. This is given. We know this from the data set. But the regression line that we fit is telling us that Y should be this much. This is Y1 is the predicted value based on the regression line. The difference between what the regression line is predicting Y will be when X is at this level and what Y actually is when X is at this level, this difference is what's left over, or what we call the residual. Okay? So the regression line is giving us the predicted values. The difference between what the predicted value and the actual value is, this is what is known as the residual. Observed Y value minus the predicted Y value tells us what the residual for that given X value is. Okay. And why is this important? The regression line that we want to fit, as it makes sense, is a line which minimizes this as much as possible for each of these values, right? So what does it mean? For a regression line to be for the prediction line to be really good, we want to reduce the difference between the prediction and the real value as much as possible. We want the prediction to be as close to the real value, right? So that is the goal of this regression line. What is the line of best fit? The line of best fit is the line which minimizes the residuals that come from the predictions, right? That the difference between the predicted value and the real value is minimized, not just for one value of X, but for all the different values of X. Okay. So the regression line is the line for which the sum of squares of these residuals, right? The sum of the squares of these residuals is at a minimum. That's a crucial element to think about it. And the equation of a regression line is given by, so the equation of the line is generally given as Y is mx plus b. So the equation of the regression line. So this hat here on top of Y suggests that this is the predicted value of Y, given this is the X value, and we need to find M and B, right? So if we can establish what M and B are, then we can find for different values of X, what is the predicted value of Y. Okay. M here is the slope of the line. It tells us how steep the line is. And B here is the y-intercept. Why is B the y-intercept? So if I set x equal to 0, B is where y hat will be, right? Where the line essentially coincides with the y-axis, where it hits the y-axis. So B here is the y-intercept. Okay? So with the regression line, there's three key elements. It's a line, so it follows the equation of line, which is y is of this form y is mx plus b, where m is the slope of the line, b is the y-intercept, and y hat here is the predicted value of y for a given x value. Given that I plug in x value here, I'll get a y value, the predicted y value. Okay. How do I find these things? And straight away you can see that it's very closely related to correlations, but it's not. The slope of the line is given by this formula, n times the sum of xy minus sigma x sigma y, but the denominator is different. It's n times the square root of x, the sum of x squared minus sigma x squared. Okay. So once you have this, then the b is just the average of the y values minus m times the average of the x values. Okay. Once you have m, which you calculate here, then you can calculate b using this. Again, make sure that you write these formulas down on a piece of paper before you start the exam, because it's important that you have these on hand so you don't, get flustered during the exam. Okay. The one crucial element is that the regression line always passes through the means of these of x and y. Wherever x bar and y bar are, the regression line is at least calibrated so that it passes through x bar, y bar, the point x bar, y bar. Okay. All of this, if it seems a little daunting, let's look at an example that we already used. We have GDP and CO2 emissions, right? And we want to find the equation of the regression line which passes through these points. The first order of business is to calculate and construct this table, right? We have x, y, we have x, y, x squared and y squared. We have the sum of these columns, right? The sum of x's, the sum of y's, the sum of xy's, the sum of x squared, and the sum of y squared. Using these, we can calculate the slope of the line. What is the slope of the line? If the slope of the line is given by n times the sum of xy, the sum of xy is here 15,573.71, minus the sum of x is 23.1 times the sum of y's, which is 5,554, divided by n times the sum of x squares, which is 67.35. Where am I getting these numbers? From this table, okay, that I just constructed. Based on this, I get, what do I get? I get the slope of the line. So I get m is, in this case, 196.15. Okay. Now, the other part of the equation is that I need to find b. B is average of y bar minus m times x bar. So what is y bar here? Y bar is the average of all the y's. So I sum all the y's up, which I know, 5,554, divide by n. That tells me what is the average of y's, right? So that's the second formula here that I've written down, right? B here is the average of y's, so add all the y's up, divide by n, minus m, whatever you found in the first part, times the average of the x's. So average of y, so the sum of y's is 5,554, I got that here, divided by 10 because I have 10 data points, minus m, which I calculated to be 196.15 times 23.1 over 10. Okay, so based on, if I calculate this out, then b turns out to be 102.29. Okay, so the equation of the regression line then is that y bar, the predicted value of y, is m, which is now 196.152 times x plus b. B here is 102.289. Okay, I just round it to the third decimal, and I get the equation of the regression line. So now that I have the equation of the regression line, I can basically plot it, right? I can just plot it. So you can just sketch this regression line. Okay. So what is this point here? This is the b-intercept. So where will this be at? This will be at 102.289, obviously. So this is the y-intercept, so 102.289, and then this basically gives me I can plot the entire line. To plot this line, I only need 2 points on this. The 2 points that you can use are obviously 0, 102.289, because that's the y-intercept. So this is at when x is 0, y is 102.289. So you get 1 point from there. The other point you can get is x bar, y bar, right? The average of x and average of y. So because we know that the regression line will always pass through the average of x and y, the point where x and y are at the average value, and you get this nice little regression line. Okay? So given that you have this regression line, you can predict, right? We have data only for some points, but what if I want to know what is the value of x when, what is the value of y, what is predicted carbon dioxide emissions when x is at 1.2 trillion. Now I don't have the data for that directly. So if 1.2 trillion, so somewhere around there, I want to know what y is. So I can use this regression equation to find what the predicted value of y is. Okay. Similarly for these values. So how do I go about it? So for $1.2 trillion, what is the predicted value of y? So if x is 1.2 trillion, so I just plug in 1.2 here, then y bar is 337.67 millions of metric tons. So when the GDP, if it turns out to be 1.2 trillion, this will be the emissions that are predicted. If it's $2 trillion, then you just plug in 2 for x. You have this equation that you just derived, and then you can predict the value for y. And 2.5 is the same thing. Okay. So prediction values, the crucial thing is to recognize is that they're only meaningful. Like you can't use this to predict somewhere completely out of the range of x's, right? Because these are the different values of x and y combinations that we have. And so if you're going to predict within this range of x's and y's, then it's okay. Because this line that we have derived is based off these values of x and y. So your prediction will be fairly reasonable. But if you go somewhere far out and you want to predict what happens when x is here, this might not be particularly meaningful because we don't have enough data sets to have confidence that this regression line actually extends there. Because if we find more data sets and this line starts to bend one way or the other, we might not have that much confidence in what is happening, right? So it might not be appropriate, for instance, to figure out what will be the carbon dioxide emissions when the GDP is 14.5. 14.5 is completely somewhere out of the data set only, right? Because the last one we have is when the size of the economy is about 4.9 and we know what the emission rates are, but 14.5 is somewhere quite out of the data set. Similarly, for something like 0.2, doesn't make sense to use this regression line to predict there because again, we might not have that much confidence in the value of the prediction. Okay, so that's basically it. With the regression, what we're trying to do is that we are observing the data points that we already have and using that to predict, you fit a line through that data set which best fits the data. What is the line of best fit? The line of best fit is the line which reduces the difference between the predicted value and the realized value, the residual, right, which minimizes the residual. And once we have the equation for the regression line, we can predict for different values of x what y will be, even though we might not be able to directly observe what is these combinations of x and y in the real world. We can now use this regression line to come up with reasonable predictions of what y will be when x is at a different value. Okay. So that's basically all we'll do. We won't get into prediction intervals and all of that because that's quite an advanced topic which is beyond the scope of this introductory class in statistics. So that's where we'll end this course. I hope if you have any questions, obviously see me in office hours or send me an email and I'm happy to help. I hope you guys had a productive semester and I think that the material that you learned in this class is useful and that you make use of it as you go forward with your lives. So that's where we'll end this course. I want to thank everyone for their participation in the course and for putting up with this new mode of instruction that we are using this semester. If there's any feedback, I'll send out an email later with, requesting feedback on the course and what you learned and what you thought worked and what you thought could be improved, and so that as we go forward and as we adapt to this new paradigm, we have more information, right? Again, I hope you enjoyed the course, learned something useful, and thanks for participating and good luck, stay safe, and I'll see you soon. Bye-bye.